In this video, we'll be looking at some more solution calculations, this time with a focus on solution stoichiometry. So when we're thinking about solution stoichiometry, this is really important because quite a few reactions are carried out with the reactants in solution. Many reactions that we deal with are not just the reactants as solids or liquids or gases reacting with another solid or liquid or gas. Most of the reactions we deal with are actually something in solution reacting with something else in solution. And because of that, we need to be able to quantitatively deal with this fact. So when we think about solution stoichiometry, all of the basic stoichiometry techniques that we learned previously still apply and are valid. Limiting reactants, grams and moles, molar masses, balanced equations, all those things still are there. When we're doing these solution stoichiometry problems, they pretty much have the same components of our other stoichiometry problems, except being we're dealing with solutions, there's this molarity piece as well. Most of the reactions we're going to demonstrate in this are going to be the double displacement reactions, just to give you a little bit more practice in dealing with those. So the first problem we want to do is actually a limiting reactant problem. This is a limiting reactant problem that kind of follows the same thing as limiting reactant problems you've done previously, except now we're in solution. This asks how many grams of precipitate are formed from the reaction of 175 milliliters of 0.640 molar sodium phosphate with 192 milliliters of 0.720 molar calcium bromide. So here again we're recognizing a double displacement reaction. So sodium phosphate reacting with calcium bromide. We need to figure out what in the world is going to get produced here. So just like we've done previously, we're going to mix and match ions. Sodium ions with bromide ions, well, that's going to make NaBr. Calcium ions and phosphate ions need to then get paired up for our other product, remembering to keep our charges balanced, -3 + 2, so you got to figure out the proper number of each to achieve charge balance for when those things combine. So that would be 3 calciums and 2 phosphates. So our new equation, after we predicted the products, so sodium phosphate plus calcium bromide, we're going to make calcium phosphate. That's one of the Ca3PO4 and sodium bromide. And again, using the solubility rules, we would have to figure out which one of these is soluble and which one of these would be the precipitate. Well, calcium and phosphate combined, that's going to be insoluble. Sodium bromide is going to be our soluble one, using those solubility rules from the solubility chart. So now that we have the correct products, we would then have to balance this equation. So that was our next step. And again, we're not showing the details of this. This is something we should be at a stage of being able to do pretty well, but our balance coefficients will now look like this. So now we dealt with this double displacement reaction. Now this is a limiting reactant problem in terms of the quantitative pieces. How do we know it's a limiting reactant? Well, when we look back at the question, we're going to see we have a limited amount of one compound and a limited amount of the other compound. We have to figure out which one's going to run out first, and in order to do that, we have to work in mole units. So in the past, you've had to go from grams to moles. Well, if we have a volume and a molarity, as we've seen, you can also get moles from that. So starting with the volume, 175 milliliters. Now we're going to use the molarity in order to figure out how many moles that will be. Before we do that, a quick milliliters to liters conversion. 1 liter, 1,000 milliliters. Milliliters will cancel. Now we have liters. To go from liters to moles, we would actually use the molarity, 0.640 molar sodium phosphate for every 1 liter. Our liters would cancel. We'd be left with the unit we want, moles of sodium phosphate. When you do that calculation, you would end up with your 0.112 moles of sodium phosphate. We need to do this with the other reactant. So the other reactant, we have 192 milliliters of the calcium bromide. Same sequence of steps. First step, milliliters to liters conversion. Our milliliters would cancel. We'd currently have liters. To go from liters to moles, we would have to use the molarity, 0.720 moles of calcium bromide for every liter. Our liters then would cancel. Now we have our moles of calcium bromide. When you do the calculation, you should get 0.138 moles of calcium bromide. So this is where we're at. We figured out our balanced equation, figured out what the precipitate is, what the products were, everything's balanced, and we just did the step to calculate moles that we had of each of our compounds. We're past the solution part of this. Okay? As soon as we got a balanced equation and figured out the moles using the concentration, we did all the solution part of this problem. This now goes back to just how we were previously doing stoichiometry. Our next step here is figuring out which one of these is actually going to run out first. Well, what's the ratio? 3 to 2. Well, that's a tough ratio. 3 calcium bromide to 2 sodium phosphate. Isn't there another way we can think of 3 to 2? And there is another way we can think of 3 to 2. Instead of thinking 3 to 2, we can think of 1.5 to 1. That's a little bit easier to deal with. So do we have 1.5 times as much calcium bromide as sodium phosphate? And the answer is no, we don't. If you kind of look at that, that ratio is less than 1.5. That's going to make the calcium bromide that limiting reactant right away. Doing the same thing we did previously when we dealt with limiting reactants. Once you have the limiting reactant, well, now we just got to figure out how much precipitate will form from that. Well, we determined our precipitate was the calcium phosphate, so now we just got to go through that specific calculation. We use our limiting reactant to figure that out, 0.138 moles of calcium bromide. We need to relate that to the product that we're going to form, the calcium phosphate, and we see with our balanced coefficients, the ratio is 3 to 1. That's going to be our conversion factor. So moles of calcium bromide would then cancel out. The current unit we're at would be moles of calcium phosphate. We're going to figure out how many grams of calcium phosphate that would be. Figure out the molar mass of calcium phosphate. That many grams per 1 mole. We want our moles in the denominator in order to successfully cancel. Moles of calcium phosphate will cancel. The unit we're left with is the unit we want, grams of calcium phosphate. When you do that calculation, you should get around 14.27, 14.3 grams of calcium phosphate. So what you should be seeing in this is that this limiting reactant problem really worked the same way as all the other limiting reactant problems you've done previously. It's just a matter of now you have solutions. So now instead of grams, you're starting with volumes and molarities, but it still works the same way. You're seeing a lot of Chapter 3 and Chapter 4 material in here. Chapter 3, a lot of basic stoichiometry things. Some Chapter 4 in terms of the double displacement reactions and being able to figure out what is the precipitate versus what's soluble. We do kind of have a new problem type in dealing with the solution stoichiometry, and that's from titrations. First, we want to talk about what does it mean to perform a titrate, or to titrate something, or to say something was titrated. When we say we're titrating something, what that really means is we're adding the exact amount of one compound in order to completely react with another compound. The whole point of a titration is such that you're not in a limiting reactant scenario. There's no limiting reactant. There's no leftovers. We're going to combine our two reactants in the exact way such that there are no leftovers. There's also a little bit different goal in dealing with titrations. Previously, we've often been focused on how much product gets formed. Generally, we don't really care how much product gets formed. The sole idea of a titration isn't necessarily to form a product, but to completely consume another reactant by adding the exact correct amount of one reactant to completely consume another one. You see these a lot. You see titrations in a lot of different places, not just in chemistry. You end up seeing it in biology, environmental studies, medicine. You see titrations coming through a lot. So here's our first titration problem. It says it takes 74.3 milliliters of 0.41 molar silver nitrate in order to titrate 86.1 milliliters of a solution of calcium bromide. What is the molarity of the calcium bromide solution? Well, first we need a reaction. And again, this is going to be a double displacement reaction. We're given the reactants, two ionic compounds. We have to figure out what the products are going to be from that. Again, I'm not going to go through the steps for this one. We're at the stage now where you got to be able to figure out what is this balanced reaction going to be. So remember, first you're going to predict the products. Then you're going to figure out what the precipitate is. Then finally you're going to balance that equation. After you've gone through and have done those steps, you should get this as your balanced equation. Remember, you got to make sure you're able to get from just the reactants to be able to get to this product line. Our next step in determining this titration is to determine the moles. Well, how am I going to do that? I got to figure out moles of each thing. But when I look at this, there's only one reactant that has enough information to be able to determine the moles. The silver nitrate, I have a volume and a molarity. That's enough to determine the moles. For the calcium bromide, all I have is a volume. That's not enough to determine moles. You can't get that just from the volume. You need more information. So the only thing I can determine the moles for at this moment is the silver nitrate. So I need to go ahead and do that. So again, I could start with the volume or the molarity. We want to start with the volume. 74.3 milliliters. I know before I use the molarity in my conversion, I would have to convert to liters. 1 liter, 1,000 milliliters. Our milliliters would cancel. Now I have liters. Now to go from liters to the moles, I need to use that molarity. 0.41 moles of silver nitrate per liter. The liter would cancel. The unit you're left with is the unit you want, moles of the silver nitrate. And you end up with 0.03 moles of that silver nitrate. So here's where we stand. We have our balanced equation. Our balanced equation is set up good. We figured out moles of what we could here. Okay? We figured out the moles of the silver nitrate. It's at this moment, this part of the problem, this is the true titration part of the problem. Okay? Figuring out how many moles of the calcium bromide we're going to need. This is that true titrate part, that meaning of the word. And what this really means, I'm going to show this in kind of green highlighter here. What this means is that what we have has to exactly match the balance coefficients. So let's look at the balance coefficients. 2 silver nitrate for 1 calcium bromide. What does that mean? That means for this reaction to completely consume itself, for these reactants to completely run out at the same time, the relationship between the silver nitrate and the calcium bromide needs to be 2 to 1. We need to make that actually happen with the moles that we have. So the moles we have of the silver nitrate is 0.03. What does that mean in terms of the moles of the calcium bromide? Well, it's got to match that same relationship. 2 to 1 still has to be 2 to 1 here. So you don't have to necessarily do the calculation. We're going to show the calculation. But you could just say, okay, I need twice as much silver nitrate as calcium bromide. I need half as much here, so that'd be 0.015 of the calcium bromide. Even if you couldn't see that in your head, you can just do a one-step calculation in order to do that. The relationship between the moles has to exactly match the balance coefficient. So what do I have? I have 0.030 moles of the silver nitrate. What's the relationship between the silver nitrate and the calcium bromide? Well, 1 mole of calcium bromide, 2 moles of the silver nitrate. And again, you're going to see the moles of the silver nitrate cancel. What am I left with? The moles of the calcium bromide. And I see that 0.015 moles of the calcium bromide. Now this matches the moles I have to the balance coefficients. If I kind of show this in blue, I need 2 to 1 for my balance coefficients. Do I have 2 to 1? Well, yeah. If I look at the silver nitrate to the calcium bromide, I have that 2 to 1. 0.030 is twice 0.015. Now sometimes people get excited, even though this was the key part what we just did, figuring out the moles based upon the balance coefficients. We didn't actually answer the question the problem posed yet. The question that the problem actually posed is, what is the molarity of the calcium bromide solution? I have enough information to deal with that now. If I think about the definition of molarity, molarity is moles per liter. Well, how many moles do I have? Well, I just calculated that. The 0.015 moles of the calcium bromide. What's the volume? 86.1 milliliters. I would just have to convert that to liters. That ends up being 0.0861 liters. I then just have to divide those values together. 0.015 divided by the 0.0861. And the result is going to give me that molarity, that 0.17 molar calcium bromide. So the key step in this calculation was setting the mole ratio that we have equal to the balance coefficients. So being titrations are a little bit of a new problem type, I want to do another example of a titration so we can get a little bit more practice in doing this. So again, this is going to be a double displacement reaction. We're asked a little bit different question, but it's still a titration. How many milliliters of a 0.330 molar solution of KOH are needed to completely titrate 24 milliliters of a 0.52 molar solution of CrCl3? So what are we being asked? Well, we're reacting CrCl3 plus KOH. We want to figure out what in the world are these going to produce. Double displacement reactions following that same pattern we've talked about in a lot of these problems. So you need to mix and match the ions. Well, chromium plus 3, hydroxide minus 1. So one of my products is going to be CrOH3. Remember, have to have charge balance. Mixing and matching the other ions. K plus Cl minus, well, that's going to be KCl. We look and figure out which one is soluble, which one's not. Potassium chloride is very soluble. Hydroxides generally are not, so that's going to be our precipitate. Then we would balance. Again, we went a little bit more quickly through the determining of the products and the balancing because we've already done a lot of that. You want to make sure you're able to get to that point. So our next task in terms of dealing with this problem, now that we have a correctly balanced equation, is we need to determine the moles. Only one reactant, again, has enough information to be able to determine these moles. And the one with enough information is going to be the CrCl3. I have a volume and a molarity for it. I have enough information. Again, start with the simpler unit. That's the 24 milliliters. First, convert to liters. So when I convert to liters, 1 liter, 1,000 milliliters. My milliliters are going to cancel. Now I'm going to be at liters. Now I can use the concentration. 0.520 molar is 0.520 moles of CrCl3 for 1 liter. Our liters would cancel, numerator and denominator. From doing the calculation, 24 times 0.520 divided by the 1,000 is going to give us our moles of CrCl3. That ends up being 0.0125 moles. So this is where we stand. We have our balanced equation. We have the moles of the CrCl3. It's now at this point where the true titration part of the problem really kicks in at. Here's the real titration part here. We need to match the mole ratio to what we have. Well, what's the mole ratio? Well, the mole ratio is we need 3 times as much KOH as CrCl3. 3 to 1 here has to be reflected in the amount we have. Being this is 3 to 1, this needs to be 3 to 1. The same thing has to happen. So we need 3 times as much KOH as CrCl3. So you'd multiply 3 times the 0.0125 moles of CrCl3 in order to get the moles of the KOH. The relationship between the moles has to exactly match the coefficients. Even if you couldn't do this in your head, and that's fine, just do a one-step conversion. Here's how much CrCl3 I have, 0.0125 moles. What's the relationship? 3 to 1. Make sure your units are canceling. Our CrCl3 moles will cancel. We're left with moles of KOH. What did you get? Well, you would end up with 0.0375 moles of the KOH. That's that true titration part. So you should go back and ask yourself, kind of show this in a little bit of blue. Does the mole relationship that we have match what the balanced coefficients are telling us? Our balanced coefficients say 3 KOH to 1 CrCl3. Do my moles reflect that same fact? If yes, then we definitely did this correct. If no, we definitely did this incorrect. Do we have that 3 to 1 ratio between the 0.0375 and the 0.0125? The answer is yes, we do. So we did this part correctly. So now I need to ultimately, we just did the key titration part of this. We still didn't fully answer the question yet. The question said how many milliliters of that solution are needed. Well, I have moles, I have the concentration in molarity. I can now figure out the volume. I start with my 0.0375 moles of the KOH. To get from moles to a volume, I can use the concentration, 0.330 molar. Now I want to arrange this in such a way that the moles of the KOH cancel out, which they do. Moles of KOH, moles of KOH. Now I have the volume in liters. Liters cancel out. It asks for it in milliliters, so just a liters to milliliters conversion. Our liters will cancel. The unit we're left with will be our milliliters, which what we want to be left with. So I'm going to just go through and do the math. 0.0375 moles of the KOH times 1,000 divided by the 0.330. That's going to give us 114 milliliters coming out for our final answer. So again, key part to the titration problem is making your moles of each of the reactants reflective of the balanced coefficients. If the ratio is 2 to 1, your moles need to be 2 to 1. If it's 3 to 2, it needs to be 3 to 2. If it's 18 to 7 or some other crazy ratio, just make it 18 to 7. Your mole relationship has to exactly match what you're seeing for these balanced coefficients. So the last type of solution stoichiometry problem we're going to do kind of goes by the name of gravimetric analysis. So let's kind of read through the problem. And it's a longer problem in terms of even the question. Kind of gives you a little bit of a story to what happened. So this problem reads, a sample with a mass of 6.51 grams contains a sulfate ion. So you have this sample, it weighs 6.51 grams, contains the sulfate ion. You don't know what else it contains. It's probably a mixture of many, many things. The only thing you know is the total mass of the sample and that it has sulfate ions. You take the sample, it dissolves in water. After that, you treat it with excess aqueous barium chloride. The resulting precipitate was isolated, dried, and found to have a mass of 1.98 grams. What we want to know is what was the percentage of sulfate in the sample. So a lot's going on here. We need to think about what in the world is happening. So without some sort of reaction, some way of thinking about this, this just becomes a very strange kind of word problem. But if you really go through what actually happened, you're going to notice this is actually fairly straightforward. So we're going to sketch out a crude reaction. So here's my sample. I got an X here. I don't know what it is. That X doesn't represent one element or one polyatomic ion or one anything. That could represent 100 different things in here. All we know is that this sample contains a sulfate ion, and we're going to react it with barium chloride. What's going to happen? Well, we know a precipitate forms. So already we're going to think double displacement reaction. That should be the reaction that kind of comes to mind for this. So in this double displacement reaction, I'm going to mix and match the sulfate ions with the barium ions. -2 for the sulfate, +2 for the barium is going to make my BaSO4. Look on your solubility chart, you're going to find that's going to be soluble. What's my other pairing? Well, X, which really represents a whole bunch of things, and chloride. So I got my XCl here. You actually can't fully balance this equation because the X is a mixture of a whole bunch of different things. Maybe molecular things, maybe ionic things. We don't know, and we don't really care. We don't have to have this fully balanced. So at this point, what do we know? Well, I know things about my sample. It's got a whole bunch of things with sulfate, and it weighs 6.51 grams. We reacted it with the barium chloride. What ended up forming? Well, we ended up forming barium sulfate. We decided that was our precipitate, and we know something about that precipitate. We know the mass of that precipitate. So the whole logic for why we did this sequence of steps that the problem started with is we're taking sulfate away from the unknowns. Remember, in the sample, sulfate was combined with all these other different things. So we're taking it away from that very complicated mixture, and then we force it into a precipitate. And we do that because we know a lot of information about that precipitate. We know the exact formula. It's one thing that we know the exact formula of. And because it's one thing that we know the exact formula of, we can actually do quite a bit with that information. So let's see what we're going to do with that. But we want to keep in mind this logic of forcing the sulfate away from this mixture with a whole bunch of other stuff and forcing it into this precipitate. So I kind of just rewrote our equation that we had up. What's happening, what our sample is, the mass, what our precipitate is, what's the mass. So there's a couple of key things we want to notice about this. The key thing we want to notice is that all of the sulfate in the precipitate originally came from the sample. So let's just think about what this means. Now I'm going to show this kind of in the blue here at the top. This precipitate, this barium sulfate, all of the sulfate there, where did the sulfate come from? Well, it didn't come from the barium chloride. The sulfate part of that precipitate all of it originated from that sample. So any sulfate that we find in the precipitate would have had to have come from that sample. That's our key thing we want to notice here, is all the sulfate went from the sample to the precipitate. Now, because we know the formula of that precipitate, we can get a lot of information on that. So our next step is to do a percent composition of sulfate in the precipitate. The total mass of the precipitate is 1.98 grams. But how much of that is sulfate? Well, let's look at our parts. So I summed up all the sulfate part, that's 96. The barium, 137.33. The total for the barium sulfate then would be 233.4. So we want to figure out the percentage composition of the sulfate in the precipitate. Well, take the part you're interested in, the sulfate, 96.07, divide it by the total, 233.4. That's going to give us 41.2% sulfate. In the precipitate, this is key. You don't want to stop here. Sometimes people get a percentage and they're so happy and excited because they know ultimately they need to find a percentage that they stop here. Well, this isn't what the question was asking. The question was not asking for the percentage of sulfate in the precipitate. It was asking for the percentage of sulfate in the sample. There's still a little bit of work that needs done here. So what we want to do is we want to apply that percentage of sulfate in the precipitate to the actual amount of precipitate we have. Regardless of how much barium sulfate you have, when you have barium sulfate, 41.2% of it is always sulfate. So we're going to take 41.2% of our 1.98. So when you take 41.2% of that 1.98 grams, you're going to get that there's 0.816 grams of sulfate in that precipitate. Okay? Why is that important? Go back a little bit to, kind of our first point, kind of what I'm showing up here in the upper left in green. All of the sulfate in the precipitate originally had to come from the sample. So if we know there's now 0.816 grams of sulfate in the precipitate, we know that there was 0.816 grams of sulfate in the sample. That's that key part. The sulfate went from the sample to the precipitate. So kind of working backwards, the mass of the sulfate in the precipitate originated from the sample. Now we're at the stage to determine the percentage of sulfate in the sample. Remember what a percentage is. It's a part compared to a total. Well, what's the part? Part's what we just determined, the 8.61 grams of the sulfate. What's the total of the sample? Well, that was given to us in the problem, 6.51 grams. Part divided by total times 100%. You end up with this 12.5%. In that original sample, 12.5% of it was sulfate. So remember the key logic here. The key logic was we forced all the sulfate from the sample, which was a complex mixture, into a single precipitate that we could then figure out a lot of information on, work backwards from the precipitate. Being we had the mass of the precipitate and the exact formula, we could figure out a percent composition of the sulfate in the precipitate, which allowed us to figure out how many grams of sulfate we really had in the precipitate. All of those grams of sulfate in the precipitate originally had to come from the sample, which allowed us to figure out what that percent composition was in that sample.